Good afternoon, everyone. It is my pleasure to introduce the speakers of the sixth Deeptails Seminar. Today, we welcome Corentin, Kervadec, and Christian Wolf. Christian is maître de conférence in the Institut National de Sciences Appliquées de Lyon, INSA, and he is leading in there the artificial intelligence chair, and he's in a team that is joined with the LIDIS CNRS laboratory. And Corentin is a PhD student under the supervision of Christian, but also he's also in Orange Labs, where he is co-supervised with Grigory Antipov and Moez Bakush, if I am pronouncing this correctly. And today we are going to be learning about high-level reasoning in vision, language, and robotics, thanks to Corentin and Christian. We are very happy to have you here today, and please go ahead. We are looking forward to what you have to say.
Thank you very much, Xavier, for this introduction. Thank you very much for this invitation to this really nice and useful seminar series you do. Thank you for the public, to everybody, to be here, because it's a very special day today, Europe's deadline. So I'm happy that somebody was actually available to listen to it. So I will share my screen. So why? Yes, here it is. Is this the correct screen? Do you see the title screen? Title slide?
Yes.
Yeah, okay. So Corentin and me will talk about reasoning, learning high-level reasoning today. We will touch various subjects, vision and language and robotics, and we split up a little bit the subjects. So I will talk a little bit more robotics, and then Corentin will talk about VQA, vision and question answering, visual question answering. As you said, we are a group in Lyon of a couple of students and me. So here is the group, not so recent picture from 1 year ago, and we work on several subjects close to computer vision, deep learning, and robotics. So we have people working on gesture recognition, pose estimation, activity recognition, and recently we turned a little bit into robotics, semantic segmentation with applications in robotics, but also human-computer interaction, navigation, etc. So the common ground, the common thread I would like to talk today is this high-level reasoning, and this is really not a task which is easily defined. So let's start with this picture, which I show since a couple of years. So when you look at this, you see a scene before and after some event, and it's pretty easy for you as a human to find out what happened here, right? So you need perhaps 1, 2, 3 seconds, but you find out that this object here has changed possession, and this has created some troubles. So what did you do here? You did not probably do some kind of easy calculations involving textures, shape, colors, which we traditionally used 10 or 20 years ago in computer vision to classify activities or objects. So you did what we call reason, and this reasoning involved, well, vision, obviously, because you look at the picture, but also you used external knowledge, you used knowledge about babies, and even if you don't have your own children, you know how babies behave. So intuitively, we understand that there was some deeper reasoning involved in common computer vision. But what is reasoning? It's really difficult to define. So if we look to some a famous machine learning researcher, Leon Boutou, who in a paper from 2014 described it as algebraically manipulating previously acquired knowledge in order to answer a new question. So what we find in here is some kind of flexibility. If you want to reason, then there is this new question formulation here. The task is probably a little bit more flexible than what we traditionally do in learning and vision. So I'll provide a couple of more examples. Vision and language reasoning. So visual question answering is the task. Corentin will talk about it in the second part of this talk. It's a task where you do some visual reasoning, but it depends on the question. So you have an input question, you have an image here, and you need to answer the agent, the neural network in our case, needs to understand the question, needs to perform some reasoning, and then providing an answer. And the question can change. We can have easy questions which are very closely related to computer vision. So how much money do I have in my hand requires me to understand what this is, where is the banknote here, and what's the term here, 10 euros. What is in this chart again? Well, here I need to read, but it can be a little bit more flexible. Like, did I leave the door open here is not just an object, it's an attribute. So is the door open and closed? Did I leave the lights on? And then you have really more complex questions which involve spatial relationship and logic reasoning. The second task is interactions with robots, and here I would like to talk a little bit about robotics. So companion robots are service robotics is the field where reasoning is really important. So we had this project a couple of years ago with the company Avabot from Lyon, where they built this small robot, and the robot is a companion, so it should interact with people. We provided the gesture recognition module, for example, for this robot, but the robot could also, for example, provide object detection and recognition capabilities, which then might be helpful to do something with, for example, this kit here. The question is, object recognition, of course, is necessary, but it's not everything. So how do we interact with people? And this is where reasoning comes in. Now, this is really a long-term project because this goes a little bit into general AI, but this is really not the field where we work in. So we would like to go a little bit more beyond computer vision. So one scenario which I really like is a very easy scenario, asking a robot to find my keys. So let's say I lost my keys somewhere. So here they are. The robot needs to find them. And if I just ask the robot a question, okay, go and find my keys, then we have the really common task of embodied question answering, which kind of combines visual question answering and robotics. So you need to answer the question, you need to control the robot needs to navigate, it needs to navigate to solve the visual task, but there is more to it. Because if you just think about it, if you ask the questions once, then the reasoning strategy the robot needs is basically exploration and on object recognition. He doesn't know where the keys are. Well, you don't know where the keys are. He probably doesn't know. So he needs to explore the environment, find navigational space, try to go to areas which have not been covered before, and then he needs to be able to discover the object. But let's just imagine that I am really a person which doesn't have much memory, and I lose my keys all the time. So if this question becomes repetitive, and after the fifth time the robot always has this exploration strategy, then there's something wrong. Because what I would like the robot to do is I would like him to understand this regularity. Okay, my master is a silly person. He loses the key all the time. Perhaps the next time I see the key, I should map it, and then I don't need to search it, right? So this is something which is already a little bit more flexible. So the robot should actually find out what kind of behavior patterns are useful to solving these tasks. Now, this is, of course, a long-term strategy, but we want to go a little bit into this direction. And what I will do is provide a couple of robotic tasks which try to make this kind of behavior emerge from training. Now, training is obviously a complex thing because what we train is not reasoning, right? We don't tell this would be supervised learning and supervising reasoning. This is really rarely what we do, apart from, oh, there will be a submission by Corentin in the next conference on this, but normally we don't supervise reasoning. So what we supervise is, depending on a task, a label, reward. Well, that's not supervision. We use reinforcement learning to maximize cumulative reward, or we supervise actions, we supervise labels, we supervise classification. We rarely supervise reasoning. And then you have this problem that if you supervise something else than what you want to emerge, you can have shortcuts. Corentin will talk a lot about shortcuts in 15 minutes. I'll just introduce a very simple example. Let's say you train a model to do activity recognition. So you provide either images or videos, and you have a couple of classes, and one of these classes is nailing. So you have a hammer in your hand, and nailing means, well, nailing, putting a hammer on a nail. And you have a couple of examples of this. And then you train the network, and your intention was recognize when I'm nailing. But this is not what you communicate. What you communicate are examples of this class. Now, if you test this on a different data set, which also includes, for example, activities like removing a nail or storing the hammer, hanging it up on the wall, and these examples were not in your training set, then it's very likely that your network will not learn how to nail, but it just detected the hammer, because detecting the hammer is quite easy. So on the test set, you will have the answer, the guy is nailing, although he's not. So I have coined this really nice term, which is easily pronounceable, and I hope which is useful in the future. No, I'm just kidding. What you get is not what you expected, right? That's the common mistake we do when we train models to perform reason. We think we train them to do reasoning, but we really don't. So commonly, what we get is not what we expected. Now, this can be negative. This is a negative example here, but actually, when you get what is not expected, can also be positive. I would like to provide two positive examples from a couple of years ago from one of my students. So this is work from Fabien Paradel, who graded it last year, and he created here a model for activity recognition. And what we had was this attention model, where you see here 4 bars. These 4 bars here correspond to attention on different hands. So each we have 2 hands per person, which makes 4 hands. And the attention mechanism places attention on the most active hand using a strategy which is learned from optimizing, obviously, only the goal, which is activity recognition. So what we expected is that high attention will be given to hands which are interesting. So this hand uses an object and gives an object to the other person, so it gets high attention. So this is what we expected. What we did not expect is that this attention model actually compensated for errors in pose estimation. So these poses are detected by the Kinect middleware, Microsoft Kinect middleware, and sometimes the middleware makes errors. So here you see, for example, the right hand is detected at some place where there is no right hand, and immediately the attention goes down here. So this is something we did not anticipate, and it was a welcome result, and we're really happy about it. But this is also the upside sometimes. So you create a model, the model exploits shortcuts and regularities in your data. Sometimes you want them, sometimes you don't want them. A second example, also from Fabien, but this is a different paper, where we had this attention model again, but this time it was an unconstrained attention model. So attention could be placed anywhere in the scene. And what you see, the rectangles here are places where the model puts attention on. And I will just stop this for 2 seconds to introduce the beginning of the video. So in the beginning, you have seen this person bending down and picking up the object. And this was actually a class. So that what we optimize here is activity recognition. So the person's bending down. And what you will see is that the person just stops, the head will look down, and immediately we'll see this one of this rectangle will immediately go to this Coke bottle. So the model already anticipates and looks at the bottle, finds out, oh, might there be a reason that this person might in the future bend down? There is an object there. Let's look there. So here it is. The person didn't bend yet, it just looked into the direction, and the model already found that perhaps I should look here. This could give me cues for classifying the activity. So the question is, if we want to learn the reason, how can we do that? And in our group, we tackle this with from various directions. Well, first of all, we need to find out whether a trained model reasons or not. So we need to evaluate data and models and find out whether reasoning happens. So Corentin will talk about this. Then I will talk a bit about tasks, because learning to reason also means during training finding out which tasks actually favor the emergence of reasoning. So that's actually quite important. Then can we create models? So some models, some inductive biases, some model structures are better for finding for reasoning, others are not. Can we work on that? Causality is quite important. Can we work on this area? Can we find out which causal links are present in the data? And finally, this is also something Corentin will talk about. It can we visualize reasoning and can we transfer reasoning? So if there is data which favors reasoning better than other data, can we pre-train on data which favors reasoning and then transfer these reasoning patterns to different tasks? So I will, for the rest of this talk, talk a little bit about visual navigation and spatial reasoning. So this is work by my student Edward Beeching, who is in the third year and is co-supervised by Gilles Demongo and Olivier Simon, by Inria actually, and me. And in this field, what we'd like to do is we'd like to put robots into places like office spaces, homes, and hospitals. This is actually the City Inria laboratory in Lyon. This is the home of one of my students. We have scanned these environments and we try to learn agents to navigate there and also to transfer these reasoning skills to the real world, to the real robots. Hospitals are another scenario, museums. So here the task is create a robot which can interact with people and solve visual tasks. Imagine, for example, well, obviously the find my key scenarios is very important, but also in a hospital, a doctor or a nurse could be required to search something. They don't want to run around all the time and fetch stuff, so that we could have a robot with wheels and grips and ask him, well, go and find some drug or something like that. So the field very much converges versus this deep reinforcement learning methodologies, and there's this common baseline where you have a camera on the robot and there's perception module, so a deep neural network, a convolutional network, a transformer or something, and which creates features. And then you have a controller here, and the controller outputs typically policy and values. You have the various deep neural baselines, actor-critic methods, etc. Since in robotics, the task is not really fully observable, it's partially observable. It's useful to provide memory. So very easy could be you could have here a recurrent neural network, a GRU, an LSTM or something, which provides additional memory. And this memory here will actually do what? Well, it creates a summary of the history of observation, which is useful for the task. So if you optimize here reward, so reward comes here something like that. And if for maximizing cumulative reward, it is useful to store some information on the history of observation in this state H here, well, then the system will try to learn. And what it will learn, and this will be the main point now, depends very much on the task. So let's talk about a couple of simple tasks which the field defined the last couple of years. So this is really a young area. Deep reinforcement learning robotics, we as a field have done this for 2, 3, 4 years. With deep learning, it has much more history with more classical methods. So point goal is one of the easiest tasks where the robot is at some position. We would like to ask him to a different position, and the robot receives at each time instant a vector, a direction vector, like a GPS, and this is obviously Euclidean distance. So the robot needs to get its direction, and what kind of reasoning does it need to learn? Well, recognize the free navigational space. Every robot navigation task needs to learn that. Recognize where I can go. Follow the direction vector, but in a very large sense, obviously, because if the direction vector points into a wall, don't go there. So the really hard part, or the harder part, is learn how to overcome obstacles. So to learn the difference between the Euclidean and the geodesic path. Find the stairs if you need to go downstairs. So that's quite easy. A little bit different is object navigation, where we ask the robot to find an object and we'll provide it with the class number, for example. Well, additionally to the reasoning necessary for the other tasks, Well, it needs to explore the environment. That's exactly what I talked about 10 minutes ago. If the robot doesn't have more information, it can't do anything else than explore the environment. That's the best strategy. Unless this object is correlated, the object position is correlated with the environment, but your car keys can be anywhere, right? Well, they are probably not in the fridge, but even that happened already. So yeah, actually, basically, you need to explore, and you need to recognize the object when you see it. So there needs to be some kind of object recognition. The next thing is, well, instead of providing here the car keys, you could provide an image of the keys, for example, or of something else here. So the task is the same, find a target object, but you provide its visual appearance. The same reasoning skills almost apply here, but the difference is now we need to recognize the object by comparing it to a target image. And here the amount of possible objects will very much have an impact on what the system learns. If you train it with 3 or 4 different objects, it will probably learn to classify them. And when you provide a new object, it will probably fail. If you provide it with 10,000 objects during training, it will perhaps learn a comparison strategy which generalizes to objects which it didn't see to training. So this is very important, actually. So the exact definition of the task is one thing, but you also need to handle the amount of objects and the amount of data and the factors of variation in data. I will come back to this in 1 minute. Next task could be same task, but the image you provide is not an object, it's a location. So for example, it could be a bathtub. So in terms of data definition, it's the same thing. You still get an image and you still need to find this image. It's just the distribution of the data is different. And now this there's a very strong correlation between the image you get and the scene. So the bathtub can't be anywhere, right? It needs to be in the bathroom. So what the robot now learns is it learns to exploit spatial regularities, room layouts. It will learn to exploit the fact that when you ask it for a bathtub and you see a glimpse of tiles in the bathtub at some observation, it will directly go there. That's possible because it has found the correlation between the bathtub and some scene of the bathroom. That's different. But the funny thing is the model is the same. And even the task definition is the same in a sense that you still get a visual appearance. So only your data distribution is different. The reasoning it needs to learn is completely different. It also needs to learn, obviously, an exploration strategy because you can't only depend on the spatial regularities, right? So what we've discovered with, so this is a task which we introduced a couple of years ago, well, last year with Edward, is the task which is supposed to be a proxy task for this find me my key scenario. So what we want is we would like to train an object, train an agent to map an object. So if an agent sees an object and the agent thinks that I don't need it right now, but I might need it later, we want it to map this object, to create a map of object affordances. And one possibility to do that is to introduce multiple objects. So this k-item scenario is what? There are multiple objects here in this, here it's 3, 4, 5, 6, if it's more complicated. And the agent needs to go and visit these objects, so touch them in a specific order. So in this case, for example, the first one, the second here, the third here. So if the robot follows this path and it has a glimpse on this object here, he sees it, he knows that he shouldn't touch it yet because it's the third in the order. Well, he thinks, okay, to find it quicker, I need to map it. He continues the exploration, perhaps or not, sees this one, touches it. Once he's here, he immediately needs to go here, right? So this task will hopefully favor the emergence of mapping. So I'll speed up a little bit. What we want the model to learn, we would like the model to generalize to new environments. And whatever the task is, some of these things, we would like them to be stored in agent memory. And some of these tasks, we would like to store them in network parameters. And the difference is really crucial. So for example, information on the scene environment, the position of a couch, for example, the position of an object, we really want this to be stored in agent memory and not in the network parameters. If you store this kind of information in network parameters, then it will overfit on the environment, and in a new environment, it will not work. Same thing for positions of objects. On the other hand, regularities of the environment, for example, the fact that bathtubs and bathrooms, no problem. Please put this in the network parameters. These are the things which we'd like to exploit in a new environment. Object affordances, well, can go here, but if it's discovered during one episode, can go in the agent memory. We don't care, but that's right. The problem is we don't choose that. We create the model. We, as a builder, we don't choose where it goes. The task formulation decides how the learned information is stored, and not only the task formulation, the number of variations in your data. And here I'll just provide this slide here. What you see here is training performance and validation performance of an agent which navigates in a labyrinth. Okay, and the different colored curves you see here are different sizes of labyrinths. So we created procedurally lots of different labyrinths, and we train on 16, 64, 256, or 2024 labyrinths. So Edward Beeching did this. If you have only a small amount of labyrinths, then your training performance is really high, and your validation or test performance is really low. Why? Because of this thing here. Information on the environment goes into the network parameters and not the agent's memory. So you overfit on your environment and you don't generalize. If you increase the number of environments, then the system can't store all this information anymore in network parameters because they're limited. It needs to learn something else. And this is where reasoning comes in, right? You don't reason here, you do more reason here. So reasoning is learned if you can't overfit on your input configurations anymore. So the agents tend to learn reasoning here. Reasoning is harder. Reasoning is harder, so the training performance is lower, but the validation performance is higher. So this is really the thing we need to do when we learn reasoning. I will speed up a little bit. What I wanted to show you is how this works for one of our robots, which we train on this k-item scenario. So this is the 6-item scenario. There are 6 items. The robot here sees one of them. It's not the one it needs to touch right now, but it stores it somehow in memory. What you see here is our memory. And this is our attention mechanism. There is query key value attention in our agent. And it continues. Here it finds one item, and the blue ball is the item it needs to find after this item. What happens is it immediately puts its attention on where the blue ball is on the map. So the attention mechanism provides strong evidence here that actually the model learned that it needed to map the object, and it attends to it, then goes to it. I will go quickly, a little bit quicker. So we also have a system where we use graphs. So the robot builds a graph and solves the task by internally following in graphs. So this is a hierarchical method which does planning on a graph level and between the graph vertices. It uses deep reinforcement learning to find the way. I'll stop here. I'll let Corentin continue. So what Corentin will talk about is visual question answering. I'll just introduce his work with one slide. So here you have an example where a system is asked, what is on the wall? Well, the real answer is here, the star, right? And what Corentin did is created a data set where all the different possible groups of questions have been collected. There are 44,000 question groups. So this has been done by Stanford. The GQ, that's the work of the GQA data set. What Corentin did, so for each one of these question groups, for example, the group of questions, all questions on objects on the walls, he created a histogram of all the different responses and their frequency. So what are the most frequent answers here? And the most frequent answers are actually, well, paintings, mirrors, and things which are on walls. Well, stars are not frequent. Stars are here. And here, what you see is state-of-the-art performance of the best models in VQA. And the best models actually tend to completely ignore the image and answer the frequent answers only. So they find shortcuts in reasoning. They don't reason. Whereas the rare answers are the ones we want. So VQA is something we do in our group, and this is really joint work. Well, that's mostly the work of Corentin and joint work with Gregory and Moise. And Corentin did lots of work on bias evaluation, visualization, and other things. I'll have a short intermediate conclusion and before I let Corentin continue. So our objective is to train agent to reason from large-scale data sets. We would like to avoid shortcuts. What is very important and which is very often underestimated is the creation of tasks and auxiliary losses in this respect. So the task defines what you learn. And it's not only the task, but also the distribution of your data. Your data can be distributed a little bit differently, and the reasoning strategy changes a lot. So we also impute neural networks with inductive biases. We try to find out how reasoning patterns can visualize. We work on multimodal inputs. And what we really want is to learn spatial representations in robotics. So how does an agent, a robot, learn a spatial representation of its environment? I'll stop here and let Corentin continue. I guess the questions will be asked at the end of both talks. Xavier?
Yes, I think, unless
Okay.
there is a very urgent question, but if not, we can wait until the end.
Corentin, to you.
Okay, thank you. So I will share my screen. Can you see my screen? Yeah, okay. So thank you, Christian. And now I will talk about visual question answering. So Christian already briefly introduced my work, so I will talk about it again. So this is a joint work with Théogénie, Grégory Antipov, Moïse Bacouche, Romain Villemot, and Christian Wolff. Because in this talk, I will talk about visual question answering, and especially I will present two papers that have been published recently in CVPR this year. So I'm going to talk about visual reasoning. So we define reasoning as algebraically manipulating words and visual objects in order to answer new questions. And in particular, we are using the visual question answering task to evaluate this ability. So this is a task which requires to handle a very large variety of skills. So basically, we design a model which is able to answer questions which are posed over images. So questions can be, for instance, asking the class of an object, the attributes of an object. It can also require to compare attributes, compare the color, compare the material, compare the size, find spatial relationships, find causal relation, logical operation. So this is a very, very diverse skills to handle. And in particular, we want to analyze the reasoning versus the shortcut learning. So Christian already talked about this. So shortcuts is a decision rule that perform well on standard benchmarks, but fail to transfer to more challenging testing conditions. And in visual question answering, we can have this type of biases. For instance, here the question is, what is the person holding? And if we look at the picture on the left side, we can see that the woman is holding a piece of paper. But my VQA model predicts that the woman is holding a banana only because there is a yellow gloves. So this is a very good illustration of the biases that we want to address. So in the first paper, which is called Roses are red, violets are blue, but should VQA expect them to? We want to address the issue of how to evaluate the dependency of the model to the VQA biases. Our first observation was that in VQA, the questions and the concepts are naturally unbalanced. So if we look at the question which are asking which kind of clothing is white, and if we plot the distribution of all the answer, we will see that there is some frequent answer, such as pants, shirt, or uniform, and there is also some rare answers, such as glove. So the goal of our paper will be to to see if there is a difference of accuracy between the frequent and rare answers. So we design a new benchmark, which is called GQA out of distribution, GQA OOD, in order to measure and compare the accuracy over both rare and frequent question answer pair. So this benchmark is designed and constructed over the GQA benchmark, which is a large benchmark with millions of questions. So we let the training intact, but we modify and introduce shift and new metrics on the validation and test set of this dataset. The construction process is quite simple. First, we divide the dataset into several question groups in function depending on the context of the questions. For instance, here we have all the questions which are asking what is on the wall. For each question group, we measure the answer distribution. There is frequent answers. In this example, there is picture, mirror, or painting, and there is also rare answer, such as star in this example. And we divide the questions into two sets, the head questions and the tail questions, depending on the frequency of the answer. And when we evaluate the different model, we can see that most of the state-of-the-art VQA model prefer to answer an answer which is frequent, even if it is a wrong answer. So we come up with 3 metrics for test and validations: accuracy all, accuracy tails, which measure questions with rare answers, accuracy head, which measure the accuracy on frequent answers. And then in the paper, we evaluate the validity of this metric. So now I propose to evaluate the state-of-the-art VQA models on this benchmark, and we will observe if there is a correlation between the frequency of the answers and the accuracy of this model. So in this plot, I have plotted on the y-axis the accuracy of state-of-the-art VQA architecture, and on the x-axis, we have the frequency of the question-answer pair. On the right side of the plot, we can see the accuracy on all the examples, including the most frequent one. So we can see that the accuracy is relatively high. But on the left side of the plot, we have the accuracy on the rarest example, and we can see that the accuracy dramatically decreased. So it shows that there is a strong correlation between accuracy and frequency of the answer. But we can also measure the head-tail confusion, which correspond to cases where the model predicts a frequent answer instead of a rare answer. So this is a typical shortcut. And we can see that the confusions increase when the examples are rarer. And it is also quite interesting to measure, to evaluate the bias reduction method, which have been designed specifically for VQA, but on another benchmark. So in this plot, the baseline is BUTD, it is in yellow, and then we apply some bias reduction method on this baseline. And we can see that on the most frequent example, the accuracy decreases. So it can be due to the fact that the bias reduction method prevents the model from learning some frequent patterns, which can be shortcuts and which are highly present in the most frequent example. However, we can also observe that on the rarest example, the accuracy is still low. So it demonstrates that this method are highly ineffective in our setting, and we suspect that this method does not improve the reasoning of this model. So we have to rethink this method to work again. So now we know how to better evaluate the dependency of the visual question answering model on the biases. But in this second paper, which is called How Transferable Are Reasoning Patterns in VQA, we want to find if there is evidences of the presence of reasoning patterns in the visual question answering model. And if there is these reasoning patterns, we want to know what is the condition for the emergence of reasoning in this model. So for this purpose, we propose to analyze the attention mechanism which are at work in transformers applied to VQA. So this issue of analyzing the reasoning patterns in transformers has already been addressed in several works. For instance, there is the paper Story of Head by Voita et al., which proposed to study if the attention heads of the BERT model have learned some specific functions, such as a function which find the position of the word, or function which find the syntactic relations between words. There is also another work which is interesting, which is Hopfield is all you need, and which studies the links between attention heads in a transformer and Hopfield networks. So in this work, we are using a vision language transformer, which is a transformer architecture similar to BERT architecture, applied to the vision language tasks such as VQA. So it takes as input visual objects detected from an object detector and question words. It outputs an answer prediction, which is a probability vector over the set of all possible answers. And then this architecture is composed of unimodal attention layers, which compute the interaction between the language only and the vision only, and cross-modal layers, which compute interaction between vision and language. And our hypothesis is that the shortcut learning in VQA is in part caused by the visual uncertainty. So we have to know that in VQA, the standard setting is the first one on the top part of the figure. So the image is represented using an object detector, which extracts all the object of the image. And then the VQA model have to reason over this set of objects. However, the object detector is imperfect. So sometimes there is objects which are not detected or falsely detected or even detected multiple times. As a consequence, the VQA model cannot learn to reason and have to learn shortcuts in order to optimize the VQA loss during the training. So we propose an alternative setting, which consists in replacing the object detector by a perfect annotation. So in that setting, we are using human annotation to estimate the object in the image. In that setting, the vision is perfect. However, it is not deployable to the real world because we do not have this annotation for every image in the world. So the goal of this paper will be to compare and analyze the attention mechanism between the Oracle model and the standard model. First, if we compare the accuracy of these two models on the GQA OOD benchmark that I have talked previously, we can see that the Oracle, which is in red, is less prone to learn shortcuts compared to the standard VQA model, which is in blue. Then, to help us in this analysis of the attention mechanism, we have designed a tool for visualizing the attention mechanism at work in the transformer. So it is Theo Jaunet which designed this tool. And in this tool, we can choose the image that you want. Then you can choose also the questions. For instance, here it is, are both the socks and the shoes the same color? Then we can choose a different VQA model. And here we have the prediction of the VQA model. But the most interesting is the colored rectangle here. It corresponds to the different attention heads of the vision language transformer. And for each attention head, we can have the attention maps here, which show the interaction which have been learned by the model. And when we look at these attention maps, we can better understand how the reasoning is processed by the model. And sometimes we can find when the model is using biases or when the model is doing a reasoning. But in the paper, we also propose some dataset level visualization. So in particular, we propose to measure for each attention head the energy distribution over the dataset. So first, for each attention maps that I have previously shown, we extract the attention maps. Then we measure the attention energy in each attention maps. For this purpose, we count the number k of value in a row of the attention maps we have to sum in order to reach 90% of the energy. If the attention is uniform, in red in this illustration, then K will be high. And if the attention is very picky, very localized, then K will be low, like in the green example. And then we iterate on all the datasets, and we plot the per head energy distribution over the dataset for each attention maps, for each attention head. Sorry. And using the Oracle model, we identify 3 attention modes. So we have the uniform attention mode, which means that the attention heads is generally uniform, similar to an averaging operation. Then we have direct attention modes, which mean that the attention heads have generally an attention which is very picky. And we have also the bimorph attention, which means that depending on the question, the attention will be either uniform or direct. And when we compare the Oracle versus the standard VQA model, we can observe that the standard model have a very low diversity compared to the Oracle. And in particular, in the standard VQA model, the attention modes are mostly uniform. Then we can also measure and analyze the relation between attention modes and task functions. So a task functions can be, for instance, filter size, choose color, query name. So in this figure, the rows represent some attention heads of the Oracle that we have selected, and the columns correspond to all the task functions. Then the rectangle, which are colored, correspond to the attention modes. If the color is blue, it means that the attention is like a direct. If it is red, it means that the attention is like an average. So we can observe 2 things. First, the attention heads behave differently depending on the function. And 2, a given function causes different attention modes for different heads. So there is a strong correlation between the attention modes and the task function. Here we have an illustration with the choose color task. So we can see here on the first row, we have selected 4 attention heads, which have bimorph attention modes when evaluated on all the examples. But when we evaluate on the choose color example only, then these attention heads have switched their attention modes and became either a direct or a uniform attention head. At contrary, when we look at the standard VQA model, which have a noisy visual input, we can see that there is no clear relationships between attention modes and the function. Then finally, we have another analysis, and we want to analyze what is the impact of the head pruning, which consists in randomly removing some attention heads by replacing them by average of the cross-modal layer. So in this plot, we have on the y-axis the accuracy, the per function accuracy, and on the x-axis we have the proportion of heads which have been removed. And if we compare the Oracle and the standard VQA model, we can see that there is a lot of difference. In the Oracle, the impact of the pruning is related to the nature of the function, and it highlights a modular property of the model. At contrary, on the standard model, the pruning seems to be unrelated to the function types. So in all these studies, we have shown that there is significant differences between the Oracle model, which have been learned on perfect data, and the standard model, which have been learned on standard noisy image representation. In particular, we have observed that the Oracle have learned to create a reasoning which is related to the task required, to the task function required to solve the question. At contrary, we do not observe this behavior on the standard VQA model. As a consequence, we propose a method for transferring the reasoning patterns which have been learned by the Oracle to the standard VQA model. So this transfer is called Oracle transfer, and it is quite simple. First, we train the Oracle model on the perfect data, and then we continue and fine-tune the training using the standard VQA data, which are noisy. And this simple transfer allows to improve the accuracy on the GQA dataset, but also on the VQA dataset, which is another dataset with human question. And it also improved the accuracy on the GQA OD benchmark that I have previously talked about. And it is also interesting because this method for transferring the reasoning patterns is complementary with BERT-like pre-training, which is widely used in VQA. So as a conclusion, we propose a GQA OD benchmark, which is a benchmark for better evaluating the biases in VQA, and so the reasoning. We propose also a deep analysis of several aspects of VQA which are linked to the reasoning. And we propose an ORAC transfer method to reduce the biases. However, there is also some limitation. For instance, our study is limited to GQA, which is a dataset with real images, but synthetic questions. And also the ORAC transfer could be more efficient because it is still dependent on shortcuts. So future work, we will try to extend this out of distribution analysis to a more natural settings. And we are also working on improving the ORAC transfer by using program prediction to regularize the transfer. So thank you for your attention, and don't hesitate if you have any questions.